Hi everyone. So today let's talk about example 3.3. So this example is very important for this chapter because all the following questions builds upon this example. And anything mentioned in this example will not be mentioned again in that book. So it's definitely beneficial to know every steps, the reasons of every steps and the derivation. So let's start it. So for the setup of this question, we have this picture. So our first test is to figure out the boundary conditions. Okay, so how about the boundary conditions? So we know that this is A. So let's look at this side. So when y is equal to A, which is the shaded area, okay, when y equals to A, we can see that the potential is 0. And what about this side? When y is equal to 0, potential is 0. And how about this side? Well, this is x equal to 0, right? So x equal to 0, the potential would be v naught. Okay. And let's see, do we have the correct setup? Yes, we have this one. Yes, we have this one. And yes, we have this one. And we're left with this one. Right? What is this? So as we can see that if x approaches to infinity, which means it's really far away from this side. So this side is the only side that with the potential. And this is potential 0, this is potential 0. So when x is very far away, we know that the potential gonna be 0 because it's so far away from this side. Okay, so now we have all the boundary conditions. Now we can use our Laplace equation. And we know that Laplace equation consists 3 variables. Then y in the book I only have 2 because we have the symmetric. So as we can see here, the z-axis doesn't matter. Why? So let's choose a random point here. Let's just say this point. Does this point have any difference with this point? They have different z-axis, right? But they actually don't have any difference in the potential. So it means that we can ignore the z-axis because the z-axis doesn't matter at all. It will not change the potential. So we ignore it. So now we are only left with 2 variables, which is great. Save our work. So now let's separate the variable. So I first assume v is separable. So v is equal to function x times function y. So notice that this is not small x, small y. Those are big, right? X, y, and y. Okay, so now let's take back all the things we have. So this is what we have. Oh, actually missing a square. Sorry for that. Okay, and for this one, because we know y only consists of y, so we can, put it out. And we can take x out equals to 0. Okay, now we have this form. Now, if I rearrange it, do it like this, now I know that there must be some constant y. Oh, haven't gone to that step. So now I need to divide it all the things by xy. So divided both sides by xy. I missed one steps. Okay. And x cancel, and y cancel. So now we have this. Oh, perfect. We have this form. So I know that they must be some they must equals to some constant y, because they have different variable. And if we are looking at x here, we can treat y as some constant. If we look y here, we can treat s as some constant, because they are different variables. So I know they have to be equals to some constant. So the left hand side equals to some constant, okay, C1, and the right hand side is the same, equals to some constant, and C1 or C2 is opposite sign, because you can see the negative here, right? So I know that C1 equals to negative C2. Okay, so now let's just make some assumption. So I just assume C1 is k squared, C2 is the same, k squared. Oh, negative k squared actually. So you might wondering why. So why do I choose C1 positive? Why do I choose C2 negative? So the reason will be very clear later. So if I do that, we have this form, right? Okay, square x, actually this, and d, and dy square. Okay, we have this. So if you learn the mechanics oscillations before, you have differential equation course before, you might know how to solve this kind of differential equations. So the solution for this equation is plus b, and the solutions for this kind of equations is this. Well, we certainly can write y in this way. As you know, this is also fine, but I don't want to do that here, because sine and cosine is easier to dealing with in this case. So I don't want this form, okay? Oh, missing some constant, but I don't want this form. So if you don't know how to solve this kind of differential equations, definitely refer back to the courses in differential equations. So now I have the general form of my solution. So let me just copy it. So why can I write this? Because I state previously v is equal to xy, right? V is equal to xy. So I'm just plugging in what I have for x and y. So x and y. Okay, now let's use the boundary conditions. You'll find that actually the entire EMM is, the core is about the boundary conditions. So it says, well, v equals to 0, y equals to 0, v must be equal to 0. So let's see, y equals to 0, and v must equals to 0. So when y equals to 0, this one will cancel, right? The sine will be equal to 0, but the cosine will left, and this is what we don't want, because we don't want it to left. So which means d must equal to 0. And let's see the next conditions. When y equals to a, v must equal to 0. So actually, let us to deal with maybe this one first, because when x approaches to infinity, you can see here this term we're gonna explode. You know, when x approaches to infinity, well, this explode. Okay, explode. So a must equal to 0. So because we don't want anything to explode. So now what do we left? We only have those two terms, right? Okay, perfect. And actually we can combine b and c to a new variable c prime. So now this is what I have. And now let's look at the second boundary conditions when y equals to a, v equals to 0. So when y equals to a, v must equals to 0, which means sine ka must be equal to 0, right? Because this is how it satisfies the conditions. And sine ka is equal to 0, which means ka must be equals to n pi, and n is any integer. Because sine n pi is equal to 0. So now we have this. Let's rearrange. What is k? K is n pi divided by a. So now this is what we have. Perfect. But from this point, it's very hard to move on, because let's see the third boundary conditions. So when x equals to 0, v is equal to v naught. When x equal to 0, so this will be 1, because e to the power of 0 is 1. We not well. We can't really do anything here because we can't use this to get our constant c. So now we need to introduce some new things. For example, if I write c equals to v naught divided by sine n pi y divided by a, and what is that? I want a specific value of c, and I don't want this form. So now we need to use the trick in Fourier's analysis. So Laplace equation is linear, so that means we know that we have this, and we can write it in a form of linear combinations, and this is also written in the textbook. So which means here for this form I can write it as v naught is actually equals to have this okay, so here what I do is just write this form in a linear combination, which means that, well, our general solutions will be in this form. So here the form becomes this because I already know what is k, right? Okay. So now let's work on the boundary conditions when x equals to 0. So now I have this. This disappear, okay, because x equals to 0. And this is equal to v naught y. So now I need to solve this equation and solve for Cn. Okay, so now let's apply an integration respect to sine to both sides. So this will be fine because I applied this integration to both sides. Okay, now I have this form because Cn is constant, so I can just move it out. And what is this? Well, let's try to solve this. So there are actually two cases when n is not equals to n prime or n equals to n prime. So let's first do n equals to n prime. So if this is true, then I would just have sine square because they're the same. Okay, and what is sine square? Sine square is actually equals to 1/2 cosine. Oh, I write this rules here. You can see here 1 minus cosine r 2x. So it's 1 minus cosine 2n pi y divided by a dy. Okay, and the first one will become 1/2. So it's this. And the second one will be 1/2 cosine. And so this will become 2 over a. And what is this? Well, this will become actually sine because the cosine's integration is sine and times the constant inside, actually the reciprocal of the constant inside, and 0 and a. Am I wrong? Oh, actually I write it opposite way. It should be started from 0 and to a. And this is 0 because when the y is equal to a, so sine 0 equals to 0. When y is equal to a, is actually sine n pi, again equals to 0. So when n equals to n prime, this integral is a divided by 2. How about n prime doesn't equal to n? So now let's look at this equation. So now I cannot use this trick because they're not equal. But I can use the cosine and the cosine transform, which is this rules. So now what do I have? I have again 1/2 cosine n pi y divided by a, actually n minus n prime pi y, and plus minus cosine n plus n. Okay. Now I have this. So we know that n and n prime is integer. So if we solve this integral, what do we have? So it's actually sine something, right? And this is also sine something. And if we look at the things inside, so it's a0, a0. So if y equal to 0, of course sine 0 is 0. If equals to a, same as the previous one, we'll find that it's actually some integer times pi. So it's again 0. So 0, 0. Okay, so if n prime doesn't equal to n, it's 0. Well, this looks like orthogonal, right? It's like the quantum mechanics. So now we have our form. So let's go back to this. Okay, so now we know that this is equal to a over 2. And the summation disappear. Why? Because there are only one cases work, which is n equals to n prime. So the summation just disappears. It goes away. So now we have 2 over a times our Cn is equal to the things on the right hand side. Okay, again, I need to solve this integral. So now I have to make the assumptions that v0 is independent of y, so that I can move it out. Otherwise, I can't solve this equation. So let's just make that assumption. So now this is what I have. And what is this? Okay, let's solve this. So this is equal to n pi y divided by a, and this. And the front coefficient would be the reciprocal of the constant inside. Oh, sorry. Okay, looks like this. Yeah. And what is this? Okay, so previously we've already proved that only when n primes equals to n, the constant value will not be 0. So we can just use n to replace the n prime here. So this is what we have, and a0, and I'm actually missing a negative sign here because the sign's integration of sine is a negative cosine. Okay. So now let me plug in the values. So when y equals to a is cosine n pi, and when y equals to 0 it is 1. And let me put the negative sign in. Okay, so this result is interesting because when n is odd number, we can see that, oh, when n is equal to odd number, for example 1, well, it's negative 1, so it will be this will equal to 2. If n is even, for example like 0 something, this will be equals to 0 because cosine n pi is 1. 1 minus 1 is 0. So we have this result. So we just take away when n equals to even because it won't gonna give us anything. So we know that n is odd, and the integral is this value. And now let's take back. Okay, so we have 2 over a Cn is equal to this. So what is Cn? Cn is, let's just put it back. Okay, so it's actually 4 V0 divided by m pi. I'm missing a V0 here. Okay, yeah, the V0, I'm missing it. V0. Okay, so now I finally know what is Cn, and this is what I want, so that I can write the final general solutions of the potential, right? Because this is just V, this is just Cn, and n is odd integer, right? And n over 1. So what I do here is I put the n over 1 inside, and I leave those constant outside. So it's like, oh, I move the constant outside, and I already know this is k, right? Also, this is k. Okay, so now this is my final form of solutions. Thank you.